before we go further, I think I should clarify one of the doubts which was asked in the last class, at the end of the class, though it doesn't concern what we are doing now, it is to do with plasticity. What is the difference between capital F and small f? I think there is a lot of confusion on this. If you notice that we had said f is equal to small f, the function of sigma, okay, minus, if you had noticed we had put sigma y epsilon bar p, and that is what we had put as 0. Note that this capital F is what we had put as 0 and not small f. Okay, I would like that to be noted. Though dou f, if I write dou f by dou sigma, okay, then that's the same as small dou f by dou sigma, because this guy here does not have any sigma, so both of them will be the same. But note that small f is not equal to 0. It is the capital F, okay, which is actually the yield surface that is equal to 0. Okay. So what is this yield surface? People still are a bit confused. Please note that it is just a geometric representation. It's just a geometric representation of this equation. That's all. You cannot obviously imagine what is there in 6-dimensional space. But if you want to imagine this, you can imagine very well in the 3-dimensional space, okay, or 2-dimensional projection of it. So for example, in a sigma 1, sigma 2, sigma 3 axis, you can imagine that it is a cylinder, and perpendicular to the axis of the cylinder, this would appear, okay, as a circle like this. So it is, of course, it is not necessary for you to imagine this. It is only it's of notional value, or just to make it easier for you to understand. We were talking about the yield surface to be like this and so on. It may be very complicated, and it's not necessary, but of course this can help you a bit to understand what it is. So it's just this mathematical representation is converted into a geometric representation, and that's what we call as the yield surface. Okay. So we'll move on now. We've seen a few of the stress measures, but before we go to some of the balance laws, which we will do maybe in the next class, we have to look at a very important topic, usually confusing to many students, though it is a very fundamental aspect of calculus, and a part of which we have already seen, which is called as linearization. If I can call it as mechanics or solid mechanics. If you bluntly ask me, linearization is nothing but a Taylor series approximation. But the way linearization is written is slightly more technical than what is written or what we can look at as a Taylor series. In other words, there are a few more things which we have to learn. And one of the reasons why I am going to talk about linearization in mechanics and the ensuing say symbols and other things that are used here is basically because most of the papers that appear today, if you want to look at research papers, and some of the nonlinear finite element books talk about linearization and have a very particular way of writing it. Okay, that's the reason why I'm going to talk about linearization in mechanics. As the name indicates, what it means is that any quantity, whatever, whether it's a scalar of a vector valued function of a vector, that's in other words a function which is a scalar which depends upon a vector x, or a vector, or whatever is the corresponding mapping that you get. Okay, it can be in any dimensional space. We call this as this belonging to a particular function space, whatever be the function space. Okay, then this can be, say for example, function of x and t and so on. This can be linearized in the sense that you can determine the value of these functions, okay, at a neighborhood, a small neighborhood around a point by Taylor series approximation. For example, given this function at say x bar, I can get the function at a small neighborhood of x bar. For example, at a point where epsilon tends to 0 or along a line T. Okay. Now, before we go further, let us write down our first statement on linearization, which comes from Taylor series approximation, so that you can write, say for example, f x bar plus say u is written as f of x bar plus, look at the symbol what I am going to write. Okay, of course you can write that as, let me write that as first the similar way as we write it, x bar u plus residues or higher order terms. Okay, linearization means simply that we are going to restrict our attention to this first term. We are not going to further go ahead with this term. Okay. So this is also written as, this term is also written as f of x bar plus df dot u plus the higher order terms. And this is called as the, look at the symbol, L of f, which means that linearized part of f. Okay. Look at this operator. This is nothing but dou f by dou x dot u. So this d, which is dou f by dou x at x bar, which is written as d bar, can be looked at as an operator which operates on f. Okay, it can be looked at as an operator which operates on f. In other words, this can be, this is, if I have x to be a vector, then it can be written as grad of f and so on. Let us define what is called as the directional derivative of a function f along, say u, same u, we will put u of f to be d of d epsilon into function, that function for which we want the directional derivative, x plus epsilon u at epsilon equal to 0. Of course, this can be we will see the connection in a minute between the two, but look at this and see what it really means. What does it mean? It means that, suppose I have a function, okay, this function is defined, say with respect to x at a point, okay, at several points, and that I want to find out how actually the function varies. See, this is just 2D, this can be say 3D, this function can be in terms of x1, x2, x3 and so on. So it can be something like whatever it is, whatever shape it takes. So what we are trying to do here is that to find out how this function varies along a certain direction at a point x. This direction along which this function varies, it's in 2D, it doesn't matter, but if it is n dimension, okay, then it matters. Then the direction along which it varies is given by u. Look at this term very closely, what we mean by this. We have put an epsilon u as epsilon tends to 0, which means that we are calculating this change of this function at a point along a particular direction. That's why it is called as directional derivative. Yeah, it's fundamental calculus, but nevertheless it's good to know this more clearly, what is meant by directional derivative. Now, if you look at this term, then I can just chain rule this. So you can write that as dou f by dou x dot d epsilon into du by, or sorry, u by, d of d epsilon of epsilon u which happens to be u. Okay, that's the just chain rolling this. So you will see that dou f by dou x dot u, which is the same as that of what we had seen as the increase in delta f in our previous expressions on Taylor series. D by d epsilon. There is no theta, t or theta. D by d epsilon of epsilon u, which is u, at we are calculating that at epsilon is equal to 0. This is not t. There is no t here. This is epsilon. Okay, is that clear? So the most famous of them is what is called as the directional derivative, and we are interested in directional derivative, which basically is one which gives us the linearization procedure, okay, and is useful to us in many instances. We will see where these things are useful to us. But before that, let me give another name to this. This is also called as Getho derivative. G-A-T-E-A-U-X, Getho derivative. Getho derivative is the word which most mathematicians use it, especially if you are studying variational formulations or variational calculus. Then, for example, Getho derivative is the one which people use. We will see why this is important in variational calculus, okay, later, maybe after we give some amount of introduction to it. So Getho derivative, directional derivative, and the increase along the direction of u, okay, it all means the same thing. We're going to introduce some more things to it, some more concepts to it, okay, called Lie derivative. We'll do that in a minute. But before that, let us see how we calculate the directional derivative of, say, quantities which are referred to the current configuration. How do you calculate directional derivative for quantities which are referred to current configuration? The usual procedure is, say, what is a typical quantity which is referred to a current configuration? Say, for example, E, Almancy strain. Okay. So if I want to calculate the directional derivative of a quantity like E, the procedure is to do a pullback operation on E, calculate the derivative, and then follow this up by a push forward operation. A pullback operation, calculate the derivative, followed by a push forward operation. So what is the pullback operation for this? So that F transpose F, right? Just check that up. So that is the pullback operation. Yes, we will see that in a minute. Why we do not do that directly? Why? What is the importance of the directional derivative like this? Okay, this is how it is defined. We are defining the directional derivative of quantities which are referred to the current configuration. So look at the way I am going to write that. So d of this dot u, okay, is the quantity which we write as a directional derivative after we do a pullback operation, and then we follow this up by push forward. So what is that I do for this quantity? For push forward, it is just F, what is it? F inverse, correct. And then what is this is the push forward operation. Push forward operation, please refer to it and tell me what this operation is. F inverse, correct. F inverse transpose this quantity F inverse. So this is the directional derivative of a tensor like strain. Now if you look at, please write this down, what would be the directional derivative of a quantity like Kirchhoff's stress, which is referred to the current coordinate, which is defined as J into sigma. Okay, what is the directional derivative, same, you do the same thing, you do a pullback operation, okay, and then do the directional derivative, calculate it, and then do the push forward. So what is the pullback operation for this? F inverse tau, then F inverse transpose, right? D U, and then what is the push forward operation? Just the opposite, F transpose. So that is how you calculate the directional derivative of these two quantities which are referred to the current configuration.
It should be F transpose inverse into
F transpose, that is called F inverse transpose.
that should be first here.
Yeah, that's what we had written here.
The second one should be before that.
This is F.
Before J. F transpose inverse.
There is no J there. What is the
With tau.
tau? F inverse tau, F inverse transpose. Yeah, F inverse is written. F inverse of transpose is usually written as F inverse transpose. Right? Yeah, this operation comes from what we had studied in the previous. Yeah, that is this is the pullback operation, right? And then followed by the derivative, and then the push forward operation. Okay, so you please note that the way we had defined the pullback and push forward operation for two different vectors, vector like strain and stress are different. We said that this is due to one being covariant and other being contravariant. But if you do not understand covariant and contravariant, it doesn't matter. Just say that it is basically because one is the conjugate of the other when we define the say stress work or work done by stress or stress power, however you view it, okay, and in which case you will understand why two are different, because ultimately my stress work should be a scalar quantity independent of whether I define these quantities in the current coordinate system or in the reference coordinate system. Okay.
Here U is the small change in displacement in the Lagrangian coordinate.
Yes. What is this U? So what is this U? So please note that's why this directional derivative is taken, okay, in the pullback operation, right? That's the thing. So it's defined in the pullback operation and U is written. Okay. Now to understand a few more things, let us define what is called as Lie derivative. Sometimes Lie derivative is what is called as Lie time derivative. You know, Lie derivative and Lie time derivative, or both of them are the same. Yeah.
Sir, we can use F to calculate the small change in displacement in the current coordinate, and after that.
No, please note. Yes, I understand what this U. Please note that what we are looking for is a small change. Okay, that is, in other words, these U defines the direction. Okay, so we are looking at the gradient along a particular direction. Okay, so it is just symbolic way of writing that I am moving in this direction. Okay, so it denotes a direction. See, that is why we had defined. Look at this here. Look at this here. It is not unit direction, but it's a direction along which you want to calculate. So that's why we had written it as a epsilon U, where epsilon tends to 0. That means that it is something like calculating the tangent. Okay. Yeah, of course. When I define it like this, they are in the Lagrangian coordinate. Okay. Now note this carefully, and then see what they are. You can see it yourself. What they are. Now Lie derivative or Lie time derivative again has a very important role in continuum mechanics. We will see in a minute why it is so. Okay. Lie time derivative is carried out like this. First, you do a pullback operation. Pullback operation of the quantity of interest to you, okay, whatever be the quantity. The next step is to calculate the material time derivative of that pulled back quantity followed by the push forward operation. Followed by the push forward operation. The material time derivative, we say we had written this in terms of d by dt, okay, of f. Right, this is what we defined as the material time derivative. You can notice that this d by dt of f can be written, I'm going to leave that as a small exercise now, can be looked at as the derivative of f along along say a velocity vector v. So dv of f is actually the material time derivative of f. So what does it mean? First of all, let us understand this physically, what we mean by this this operation, or what does this mean, or why is lead derivative important. We'll just show that in a minute, but let's understand the physical significance. What is the significance of this statement? That it is the derivative of this quantity along a particular vector v. So what is this pullback, material derivative and push forward operation? What it really means, the question which you asked. It simply means that if I take a quantity, okay, and I want to know how this quantity itself varies, say this f varies, okay, as it moves along say a particular line or particular velocity, okay, then what I should actually do is to travel along with it, okay, in that particular velocity and along a particular line and see how this quantity varies. So lead derivative, physically what it means is that it is a quantity which comes out as I move along with the particle with a velocity, okay, along the direction in which it moves. So it removes all the other external things and it gives me only how that quantity varies, or in other words, the lead derivative gives me an objective quantity independent of the observer motions. So that is the importance of this quantity, that whatever be the velocity, whatever be the direction in which it is traveling, it gives me the correct flavor of how this quantity changes. Okay. So you will see that you will see maybe in the next class that lead derivative gives me a quantity which is one which can be used directly in what are called as constitutive equations. These are quantities which can be used. Lead derivative gives me quantities of certain of these derivatives, time derivatives, which can directly be used in the constitutive equations. In order to understand this, let us say we will do a small exercise. Calculate the lead derivative of Almansi strain. Calculate the lead derivative of say Almansi strains. Okay, look at this definition here and then do that. Let us see how you do this. Just calculate that. Yeah, you know all the formula, what all we have done. I want you to refer to it back and then tell me what this is. The Lie derivative. Note that df by dt is nothing but dou f by dou t at a particular x, okay, and just we can calculate that. What is the pullback operation of E? What is that you will get? Yes, no, what is this quantity? When you pull back small e, very good. So that's all. So the pullback operation gives me capital E. Okay. Then what is the material time derivative? I wantonly gave this and I wanted you to think, what is the material time derivative of E? What is the material? Please note we had two things, spatial time derivative and material time derivative. Okay, the two things that, so d by capital D by t dt. So this is what we are saying. So this quantity, what is this?
Dou E by dou t.
Yes, so that is d by dt, d of capital D by dt. This is not equal to dou by dou t of E plus grad, if you remember grad E dot it is not equal to this. That's the reason why I gave this, because this is only for a spatial quantity's material time derivative. E itself is a material variable. It is defined in terms of the Lagrangian coordinate. So it is in the reference coordinates. So obviously the material derivative of a quantity like E is E dot. Yeah, E dot, straight away it is E dot. Okay, because I have pulled back, I have got E, capital E, which is E dot. Now what is the next operation that I do? I give a push forward operation. A push forward operation of this quantity. Fantastic, that's a good answer. So what you get is small d. Small d. So the Lie derivative of small e is small d. Okay. The material derivative E dot. See, E is a material quantity. Okay. So that means that it is defined with respect to capital X. The F transpose F and E is equal to half of F transpose F minus I and so on. So we said that there are two quantities for strain. This is the Lagrangian quantity and the other one we defined as the Eulerian quantity small e. So we also defined that E, when you pull back we get capital E. Okay. Now when I want to take the material derivative, there is no need for me to do velocities and other things to go into my calculations, okay, because it's a material quantity. So I can just say it is E dot. Okay. Then I do a push forward operation. So F inverse transpose E dot F inverse, which is equal to D. So the Lie derivative of small strain E is equal to D, okay, which is the, what is this? The symmetric part of the velocity gradient tensor, or we call this as rate of deformation tensor. We call this as the rate of deformation tensor. So this rate of deformation tensor is going to be very useful to us, and it participates in many of the constitutive relationships, because basically this quantity, okay, is free from the observer's moment. We are going to see what it is, or objectivity, in the next class, but before that we understand this as well. Is that clear? Okay. I leave this as an exercise. Just calculate this, okay, what dv in terms of velocity. If you do not understand, we will come back to that later. Okay. Now Where is this? Okay, we will talk about lead derivative again once we have defined it, we have seen physically what it is. We will come back to it when we talk about constitutive equations. But now let us understand directional derivatives and where we use directional derivatives, or in other words, Getho derivative. Directional derivatives have two roles for us. One is, the most important role is in our minimization of functionals. Minimization of functionals. In fact, the minimization of the functional is defined through, actually through the directional derivative or Getho derivative. Okay. We had sort of did not look at it so very carefully when we did the first course, but actually we have to look at that more carefully now. Why is Getho derivative becomes important when we do a minimization problem? Basically because if I have a function, look at that, if I have a function or a functional, it's a function of say u, okay, whatever be that u, and u is a vector quantity, u may be a function of x and so on, then I have to calculate this phi, okay, to be a minimum whatever be the direction. Say for example, just to say that, say maybe say this functional may have, it may be something like a, say yeah, a vessel like this. So in whatever direction I move, okay, perpendicular to this plane or so on, this particular function, okay, has to be minimum, or the directional derivative, whatever be the direction, should be equal to 0. Hence the importance of the directional derivative or Getho derivative. Is that clear? So geometrically you can see that this derivative gives us all the aspects that you would see in just a function whose minimization we had carried out, for example, by just differentiating it with respect to x. Because we had only, say for example, some y is equal to some function of x, then we do not have this kind of problems, because we can just state dy by dx, okay, to be equal to 0, because we just have a nice graph like that, and then you want to calculate what is the minimum for this kind of thing, then it is simple. But now when you define a function, okay, with u which can vary, or which can vary in n dimensions, or it can have n dimensions, then we do this minimization problem by defining a directional derivative or a Getho derivative. Okay. Now before we go further, let us look at certain other quantities, okay, which is of interest to us. Now let's see that. I mean, before we go into the details of the minimization problem, we have to look at certain other aspects. Now let's take a quantity like E. Okay, we had calculated the material time derivative of it. That's fine. But what is this dE, or how do I linearize a quantity, a kinematical quantity like E? Because this is going to be important for us later to define this in the either in the potential energy theorem or later in the virtual work principle as the next step. So what is the linearization of E, or along a direction u, how does E vary? So we know that E is equal to half of F transpose F minus I. So what we want to find out is half of F transpose defined for a particular configuration plus, say, epsilon u along a certain direction, and I think I have to define d by f of chi plus epsilon u minus I, the whole thing taken at epsilon is equal to 0. So what I have essentially done is to just say that we have defined the directional derivative. Or in other words, what we are trying to say is, what is the linearized part of E? Okay, linearization of E. You will notice later that, say for example, this can be defined at E bar at a point, okay, or at a configuration rather, plus say delta E bar, plus higher order terms which we are neglecting. Okay, and just bear with me for 2 minutes, then you will understand the whole thing. Okay, this delta E bar is nothing but d dot u. In order to do that, I have to know, I have to calculate, okay, this the linearized part of f, which is the deformation gradient tensor. So how do I do the linearized part of the deformation gradient tensor? Or in other words, what is the df dot say u? How do I do that at a particular configuration chi? So this is given by d by d epsilon of dou of epsilon v at a particular configuration, dou x at epsilon is equal to 0, which can be written as d by d epsilon with respect to small chi or small x, we can do that. So f plus epsilon into grad, sorry, not u, grad u at epsilon is equal to 0, which gives me grad u. So in other words, this expression can now be written as, look at this expression and look at that, the what we have got now, and so substituting that, you can say that the linearization of E with respect to u can be written as half of f bar transpose. F bar indicates the calculation of f for a configuration given by chi bar. If say what we mean is, if this is the reference configuration, we are linearizing E with respect to a configuration given by chi bar, okay, into the other part is given by here. So the what we have done, so it's given by grad u plus grad transpose u f bar. Yeah, what we have essentially done is to replace, see this, when I differentiate it with respect to epsilon for this, so this is constant, differentiate this, then again, of course, I is going to be 0, then again differentiate this, and that is, say, d of uv, that's all. That is what we have done, okay. So this gives me the, what we call as the directional derivative of E along u. To understand that, that's why I said just wait for a minute. Suppose I take the reference configuration as the configuration and do a linearization of E, let us see what you get. So at reference configuration, this chi bar is equal to, or small x is equal to capital X, okay, which means that f is equal to 1 or I, which means that the linearized part at the reference configuration x of this will give me half of grad u plus grad transpose u, because it's at the reference configuration, okay. That means that this fellow coincides with this, which means that this f bar calculated at the reference configuration itself, that means there is no deformation or no change, so it is I. So when you substitute that, you will see that linearized part of E is equal to half of grad U plus grad of transpose of U. What does this mean? What is this? It is, what's this? Very simple. No, it's not L. No, there is no E dot. U is just a displacement, because in this case it happens to be a displacement. Epsilon, small strain. This is nothing but half of grad U is dou U by dou x I plus epsilon. What does this give you? What does the statement in indical notation means? Indical notation, it simply means that this is equal to half of dou ui by dou xj plus transpose of this dou uj by dou xi. Okay, and this is what is our definition for small strain. Okay, so this happens to be just a small strain. So in other words, what this means is that the linearization of our large strain actually leads to small strain. Is that clear? The linearization of our large strain really leads to small strain. So in order to understand this, I know it will take some time to sink in. We will do that again in the next class. But in order to understand this, let me give you a small problem. Why not you do a small problem? Assume a scalar field. Okay, we will get used to this directional derivative. So maybe some of the things I will repeat it again. Let us do this problem and get more familiarized with how to calculate it, and when we apply it so that it will become easier. Assume a scalar field to be defined by x1 squared plus 3x2 x3. Okay, assume the scalar field. Let it describe some physical quantity in space. Compute the directional derivative. Compute the directional derivative of this quantity phi. Okay, along the direction u. See, look at that. I am giving you a direction. So along the direction u, say, which is given by 1 by root 3 of E1 plus E2 plus E3 at the point x given by 2 comma minus 1 comma 0. So the first, is that clear? At the point x. So this is what we call as x bar. At the point, when I say at the point x, that's what we mean by x bar. Now the first step is for me to calculate x bar plus, say, t into some, or epsilon into u. Okay, and calculate phi along that line. So what is this x bar plus epsilon u in this case? This happens to be 2 plus 1 by root 3 minus 1 plus 1 by root 3 comma 1 by root 3. All of them has, of course, that's the epsilon, epsilon in it, into epsilon, into epsilon, into epsilon. So 2 plus 1 by root 3 into epsilon, that is epsilon by root 3, minus 1 plus epsilon by root 3 comma epsilon by root 3. So this is what is my x bar plus epsilon u. So what do? I now substitute this into that expression. That's my next step. So substitute that into this expression and then calculate d by d epsilon okay, of this, what is x1? So 2 plus epsilon by root 3 whole squared, right, that is x1 squared, plus 3 into x2 x3 is minus 1 plus epsilon by root 3 minus 1 plus epsilon by root 3 into x3. What is x3? x3 is epsilon by root 3 epsilon by root 3 at epsilon is equal to 0. Okay, this is what we mean by the directional derivative of phi. That is, what is its increase along the direction of u. Why do we do this? This is derivative along u. When you take epsilon equal to 0, that means just at that point. That's what we mean by that. Okay, by that particular derivative. So what's the, please calculate this. You would see that this is also equal to grad phi. Okay, grad phi. Just look at that answer, and also you will see that this is equal to grad phi dot u. Then this is what we saw also as the directional derivative. What it means, grad phi is that is the derivative along. What is grad phi? So this is nothing but dou phi by dou x1 into, that is E1 plus dou phi by dou x2 into E2 and so on. So it is the derivative of this along dot u. That means that it is the derivative of this along the direction of u. You would see both of them are the same. Okay. So directional derivative, in other words, for this case, you can also calculate, you can say that the directional derivative along any, say, vector u can be calculated from grad phi, that is the derivative along the basis E1, E2 and E3, and then take the dot product of it along u. Right? Okay. You would see that this forms the basis for our minimization problem also, this minimization problem also for our potential energy theorem. So we will stop this, we will continue this topic in the next class, maybe zero in on certain things which we are supposed to know on potential energy theorem and virtual load principle. Okay.